This summer I wanted to build an experiment with switch mode power supplies, and to do that safely I decided to build a simple isolated linear PSU. Its output voltage of around 35 volt is much safer than 325 volts of rectified 230 volt mains. More importantly, the transformer used provides galvanic isolation, making electric shocks less likely. Also, I will be able to probe around with my mains reference oscilloscope without worrying about shorting anything out. So let's take a look at what it actually takes to build one of these. From the left, we can first see the schematic symbol of a transformer, which basically takes one AC voltage in and transforms it into another AC voltage at the output. To go into a little bit more detail, the input is connected to a coil called a primary. Alternating current going through this coil creates alternating magnetic field, which is trapped by the core on which the coil is wound. This magnetic field induces voltage in another secondary coil, also wrapped around the core. This is an efficient way to step voltages up or down and electrically insulate the output from the input. One thing to consider is that for a transformer to work correctly, its core must not be allowed to saturate, which means that it has to be sized accordingly. Excuse my oversimplification here, but as the energy is transferred to the core in packets, if we increase the frequency of the input AC, it's possible to achieve the same transformer power with smaller energy packets, meaning smaller maximum magnetic fields through the core, meaning smaller and lighter cores. And in the old days, if you needed lightweight equipment, as in the aircraft industry for example, where every ounce of weight counts, you would use 400 Hz AC instead of the usual 50 or 60 Hz, like in this old portable oscilloscope. Actually, even now, in modern switch mode power supplies, transformers are used, but with frequencies reaching hundreds of kHz. It's not all roses and unicorns, however, as it's much more difficult to minimize eddy current losses at those frequencies. The transformer I'm going to use today has a center-tapped secondary, meaning that if we use that center tap as a reference point, when voltage on one of the other taps is positive, voltage on the other one is negative, and vice versa. Taking a look at the actual unit, you can see that after soldering a mains lead to the secondary, I hot glued it in place, both to provide some insulation and to act as a strain relief to the cord. This transformer has many coils on its secondary side, but the center-tapped coil we are looking for is attached with the thickest copper wires. Also, the center tap has two wires attached to it. So once we have a smaller AC voltage, we need to rectify it, that is to make it DC. The simplest way to do that is with PN silicon rectifier diodes, because as the name suggests, they are built for the job. Looking at the schematic symbol of a diode, the only thing you need to know to match it with the real-world counterpart is that the vertical line in the symbol matches the line that's on one of the sides of the diode. Technically, when it comes to diodes, one side is the cathode and the other is the anode, but those terms are really easy to mix up and nobody uses them anyway. When it comes to what a diode actually does, well, I am oversimplifying again, but it lets current pass in one way and blocks it in the other way. The diode symbol kind of looks like an arrow, and if the current direction matches the direction of the arrow, it will be allowed to flow, like on the left here. When polarity is reversed, however, then no current flows. Again, huge oversimplification, but let's move on. So now let's look at the simplest rectifier. Only the transformer's secondary sign is drawn here, but just imagine that the rest is there as well. Okay, so if we use the bottom tap as reference here, then the top one alternates between being positive and negative. The positive half goes through the diode, and the negative half is stopped. Let's see that in action. The yellow waveform is the transformer's output, and the pink one is the output of this single diode rectifier. Seeing that, it's not difficult to realize why this type of rectification is called half wave. If we want to achieve full wave rectification, one thing we can do is take a center tap transformer and perform half wave rectification on both the top and bottom taps. Since they are positive at different times, they are in antiphase, different halves are rectified, and after shorting their outputs together, we get full wave rectification. Take a look at the blue waveform, that's the other tap rectified. Another thing we can do with this two-diode rectifier is to change the diode's orientation. If you take a moment to analyze it, it's pretty easy to see it will also act as a full wave rectifier, but the output waveform will be all negative. There's nothing to stop us from putting those two in parallel and getting both positive and negative DC on the output. In fact, we can just do away with the ground and use a simple winding without a center tap and use the negative output as ground. That 4-diode arrangement is sold pre-made in many different shapes and forms. Actually, that small black diode from before could handle only 1 amp of current, compared to this rectifier here, which can handle up to 50 amps. Okay, the last building block I'm going to talk about today is the filter, because as you saw, rectifier output is not real DC. It is only positive or only negative voltage, but it isn't really constant. One way to fix that is to add a capacitor on the output. It is charged by the rectifier when its output voltage is high enough, but when it goes down, it is the capacitor's task to keep the output voltage relatively constant. Choosing the filter's capacitance is pretty easy if you know what you're doing. So let's analyze this case. Okay, so what you can see here is the capacitance C on the left with a resistive load on the right. As we know that the capacitor is going to discharge very slightly, let's just assume that the current that's drawn by the load is relatively constant. By the very definition, the intensity of electric current is the rate at which charge flows, with respect to time. In our case, the aforementioned charge means charge flowing out of the capacitor. Continuing, capacity of a capacitor is the ratio between the charge it has accumulated and the voltage across its electrodes. Rearranging that, we get the formula for charge given capacity and voltage. So, substituting that for charge in the formula for current, we get current equal to capacity times the rate of change of voltage with respect to time. Because we are analyzing what happens every, let's say, 100 milliseconds, as the capacitor is charged up to some voltage, and then it needs to sustain that voltage for another 100 milliseconds, while the load is drawing some current. Let's change that derivative to the quotient of two averages over that time period. As we assume that the current is constant, we can rearrange things a bit and get the formula we were looking for, namely, what capacitance do I need to use based on my load, AC frequency, and maximum ripple voltage. Now that that part is over, let's build this thing. The things I'm using are some wire and wire strippers, crimp terminals, nuts and bolts for securing everything together, as well as copper clad laminate, that's just what I had lying around, full wave bridge rectifier, two big polarized electrolytic capacitors, and obviously the transformer. Let me check if everything will fit. And yep, it's alright. Take a close look at the capacitors. I'm mounting them upside down, which will block their vents, and that's never a good thing. Especially since I will screw this up and wire one of them backwards. Luckily it won't blow up, and I'll live to learn nothing from the experience. Anyway, after marking and drilling, both the transformer and rectifier are attached safely to the laminate. Now the only thing left is attaching the capacitors and the wiring. After lots and lots of soldering and crimping and hot gluing, I'm ready to notice that I shorted out some transformer tabs. After fixing that and not realizing I had wired one of the caps wrong, I get ready for measuring the output and then I plug in this contraption from a safe distance. I heard some quiet crackling right after I plugged it in, so I disconnected it a couple of seconds later. I went to check the capacitor's temperature, and sure enough one of them got hot. When I saw which one it was, I realized my mistake. You see, that big white stripe on electrolytic capacitor is the negative electrode. Usually you just connect it to ground, but this is a symmetric power supply, so the blue wire is negative, way below ground. The embarrassing thing is that this is almost the absolute simplest power supply one can build, and I screwed it up. It's only those who do nothing that make no mistakes, I suppose. Anyway, after fixing that, it's time for testing. Let me attach my meter to the positive rail. You can see that with no load, even after turning off the power, it's pretty slow to discharge. Surprisingly, the negative rail behaves the same way. I was certain I damaged that capacitor severely, but I guess I was quick enough to prevent any permanent damage, at least when it comes to leakage. While the capacitors are still charged, let me show you a cool effect. I'll measure the capacitor voltage while and after I discharge it. So as you may expect, discharging through a resistor results in exponential fall, but the interesting thing is that when I stop discharging it, the voltage starts to climb back up. This phenomenon is called dielectric absorption. While in this case it's just something cool to observe, if you're dealing with high voltage capacitors and are not aware of it, you might get a nasty shock from a discharged capacitor. Now it's time to test it under load, and to do that I'm using a 100 ohm resistor rated for 25 watts. Quick calculations show that with 35 volts across it, it will have to dissipate around 12 watts, so it might get pretty hot. Anyway, I'm soldering it in because I don't really have a better way of attaching it right now. As I only have one resistor, I'm going to first test the positive rail and then the negative one. You can see the output voltage on the oscilloscope. It's almost 35 volts with very small ripple on top. Here I'm touching the resistor to check its temperature, but because it's just after turning the power supply on, it didn't have enough time to heat up. And I didn't realize that, so expect fingers being burnt later. To see that ripple better, I'm going to AC couple that scope channel, which will remove the DC offset and allow us to take a look at only the ripple. You may not be able to see that very small measurement text on the oscilloscope, but it says 380 mV, which is roughly 1% of the output voltage. Not bad, and more importantly, it fits the formula we derived earlier, as the capacitors are 10 mF each. Also, the shape of the ripple is quite nice, as it looks like just two lines repeating, but actually that's the very top of a sinusoid, and then it's the very beginning of an exponential fall. One quick resolder later, and you can see that the shape on the oscilloscope is more or less the same but inverted. Unfortunately, the scope recording got damaged, but yeah, the ripple was the same on the negative rail, proving yet again that the capacitor did not get damaged. Neat. Too bad I melted part of my scope probe hook. I'd like to quickly mention here that I should probably add some fuses on the input and the output, but again, I'm too lazy to do that. So that was my first video. Sorry for the poor quality in places and any potential mistakes I made, but everybody's gotta start somewhere. Now I leave you with a footage of me not blinking for 45 seconds.